even if it takes a nano or picosecond to try one possible conformation, this much possibility would cause the protein to use a long time to get to the final, that only one possible conformation. Okay, so this how long is that time? That time is even longer than the age of the universe. Okay, so that doesn't really make sense. So if we use this estimation, that would mean the protein would take the universe, the age of the universe, that long time to find its most stable conformation, which is not the truth. Right? It takes only milli to microsecond to find the minimum most stable conformation. So that is the paradox he brings up. So why it is so quick to find the conformation, to find the best conformation when there's so many possible. So actually, the reason is that the assumption of this paradox is that the protein fold from a random conformation, so it doesn't have any bias when it starts to fold. But actually, that's not true. So because proteins, they fold from a denatured state that's already sort of very similar to the final state. Even when the protein is first born, it already takes some sort of conformation that is close to the most stable one. So that's why it doesn't need to try so many different possibilities to find the optimized conformation. So it would take much shorter times. Okay, so why it's so difficult for us to accurately predict a folding, like how the proteins will fold? First is even though we know that we know some denatured states, there's still many possibilities. The number is still huge. So the simulation are computational, very expensive, and in nature, the nature has many other ways to help it to find the minimal, to find the most stable state, like post-translational processing. It has some chaperone proteins to help the protein to fold, but in computer we don't have any of these helpers. So all we can do is to calculate the energy in a robust way. So we don't have any other tricks to do. So that enhances the difficulty a lot. And so that's why, so for example, some people estimate that with the current computational power, the protein fold on the tenth of microsecond time scale, but it would take 10,000 CPU days to simulate the folding. So that would means 30 CPU years. So that's a very long time for us to wait to get one structure out. So it's not feasible for us to, so that's why without a better way, currently we still cannot get a very good protein structure prediction just from pure computational calculation. Okay, so this slide just shows that there's too many possibilities. We are assuming 100 amino acid protein just now, but most proteins are much larger than that. So for 300 amino acid proteins, there would be like many different possibilities for the folding. So it's a very complex and difficult problem to solve to predict a correct protein structures. So and in a biological way, we don't see that many proteins. So people are asking why there are not that diverse proteins as we have predicted. And the reason for that is twofold. One is a convergent evolution. So that means even though we have the proteins are large and theoretically there should be many different diverse proteins, but they are sometimes they have similar sequences, so they fold in the similar 3D structures. So we will see many proteins that will have the similar 3D structures. And also from evolution, most proteins, they come from just a few ancestors. So they evolve from the same ancestor and they will diverge into some certain ways. So they won't diverge into a random, they will not randomly change their sequence. So all the proteins we see right now, they will have some extent of similarities. So that also decreases the real number of the existing proteins. But even for those limited number of proteins, it's very hard to predict the structure of every one of them. Okay, so since it's so hard to predict the structure itself from scratch, is there any other way around that we can sort of solve this issue? So one way, before the development of AI, people use a homology modeling methods to get an estimate of the protein structure. So that means if you don't have a experimentally available structure for a protein, maybe you have some similar sequence of your protein which has available structure. So in this case, you can overlay your protein to that available structure and get a estimate of your unknown proteins. So that depends on a basis that if two proteins have a similar sequence, they should have similar structure. So basically, the structure of a protein is completely determined by its amino acid sequence alone. Okay, and also there's a second assumption behind this is that with evolution, the structure changes more slowly than the sequence. So basically, similar sequence may very likely adopt the same structure. So based on these two assumptions, we can use this homology modeling method to predict some unknown protein structures. For example, the TX19 is a human protein without structure, so it's experimentally challenging to solve it as well. But people found that there is this protein which has a code number of 2AAM. It has crystal structure of a protein from a bacteria. And these two proteins, actually, if you align them, they actually have very similar amino acid sequence. Okay, so you can see those stars shows a very similar amino acids. So you can see they're quite similar, so that you can use the BLAST tool to see the similarity of the two proteins, like in what extent are they similar together. So this is an NCBI tool where you can input the sequence of the two proteins and ask the software to calculate the similarity between the two. So if you get a like 60 or 70% similarity, that means a pretty high level of similarity. Okay. So people found that this tool has pretty similar sequence, so that they can use the homology alignment to predict the unknown structure. So basically, the green one is the known structure, and the red one is a unknown without a known structure, but we can align the sequence on top of the green and get a estimate of the final folding, how it folds. Okay, so that's a way that people usually use to at least to get a sense of how the unknown protein will fold based on the homology. Okay, so right now there are actually more powerful softwares that can really give us the predicted structure from scratch even without some homology model. So a Swiss model actually is the one that utilizes the homology modeling methods, and also we all know that AlphaFold can also show us the unknown protein structure by the deep learning methods. So people already train it with many non-structured database, so that it can has a very high accuracy of predicting unknown protein structures. So the AlphaFold, this is the one that I found last year because it developed so fast. Right now, we already have the AlphaFold 3, which not only give us protein structure, but it also can predict the protein and other micromolecule interaction. So basically, we can also get the structure when our protein is in complex with a DNA or RNA, for example. And that is important because many proteins, they are DNA or RNA binding proteins. So it's important to know how and where it binds on the DNA. So with this machine learning and deep learning methods, people are now have higher and higher capabilities to predict protein structures and protein complex structures. So I suggest you can go to the AlphaFold 3 website to try it out, and you can try it predicting some sequence you input in. You can input one that already have available structure in the PDB database, and you can compare the prediction results of AlphaFold 3 with the experimental structure and see how close they are. Right? So you'll be like amazed by its capability. So it's a very powerful tool right now. All right, so let's take a 10 minutes break, and then we'll continue with the rest of the slides. And if you haven't downloaded the software, you can use the break to download and install the software.